Okay, hi everybody. I'm Tom. I'm also going to speak about Cholesterics, but I'm going to take a slightly different approach and talk about how we can use a mathematical theory called contact topology to understand them, or at least understand parts of what they do. So Randy already went through this, but I'll just go over it again briefly. So Cholesterics are a type of liquid crystal which have chirality. Their ground state, Randy, where's the button for the light on here? Is it the green thing? Yeah, okay. Their ground state is given here. So you have these molecules that lie in these planes, and then as you travel perpendicular to the planes, the molecules twist with a characteristic speed, and there's a length scale along which they twist by 2 pi, which is the pitch. And in general, so they look like this, and you get these defects. They're very, very complicated. And in general, the energy of these systems is governed by the Frank free energy. So there are these 3 terms. There's the splay, the twist, and the bend. And there's also saddle splay, which I've neglected here. And the important thing about the cholesteric is that you have this Q0 term here in the twist, which means that the ground state, which is given here mathematically along the x and y directions, and z is the pitch axis, the ground state satisfies n dot curl n is minus Q0. Okay, and that's the energetic requirement that the cholesteric wants to sort of have everywhere. So this is the ground state, but as sort of suggested by some of the things that Randy spoke about, cholesterics do all sorts of stuff. So here is, again, Lisa's experiment, where just in the one system of the cholesteric shell, you get all these different textures, all these different types of configurations, so various stripes and focal conics and planar things. And not only do you have loads of textures within, loads of 4 different sort of classes in their experiment, but actually each class has many different realizations, and many different ways I can pack focal conic domains or pack these stripes or these stripes. Okay, but not only in cholesteric shells, but I can also look at droplets. This is one of many papers on droplets. Again, this is just a small selection of the huge number of crazy things that cholesterics do. You also get to these lovely networks of defects, or these streak textures. We can also look at some other stuff. For example, cholesterics can also do things like can make topological soliton structures related to the Hopf invariant. They can also make these polygonal textures, these fingerprint things that we've seen. These are sort of when we're looking sort of at the layers. There's also this recent work which is done with some colleagues from Bristol and also Machon, where they made these skirmion bags in cholesterics as well. The point I'm trying to make is that cholesterics make a whole load of stuff. There's like a whole load of things they make. You choose a particular geometry, boundary conditions, and then you see what they do, and they typically do a whole load of stuff. It's always very complicated, takes a long time to figure out. And sometimes, sometimes they look like layers, but sometimes they don't make layers. Sometimes they do all sorts of different things. And what I want to try and understand, the basic question is, can we understand why the tendency of the cholesteric to twist leads to such morphological richness generically? Can we understand why, generally speaking, we would expect a cholesteric to produce such a huge variety of states? You can instead phrase it from like an energy landscape perspective. Why do I expect generically the energy landscape for a cholesteric to have many, many local minima? That's the question. All right? Or you can say, what is so special about this term? Okay? What is so special about the fact that this term that leads to this very rich behavior? And I want to give a very simple example of where you find such an energy barrier, such multiple metastable states. This is not meant as this is like the simplest example I could think of. Okay, so this is the Helfrich instability. We have a cholesteric between 2 parallel plates. Boundary conditions on top and bottom are the director field lines sort of tangential to the plane. I've set it up with a 1 2 pi twist in it. But the ground state of this system wants to have 3 2 pi twists in it, so it's frustrated. Okay, so the twist, the n dot curl n has the wrong value. Okay, and it turns out that if the frustration is high enough, there's an instability, the Helfrich instability, and if you add in a sinusoidal perturbation to the layers, that will grow. So you can work out various thresholds depending on the elastic constants for this. And if you study this instability, you'll see that what the cholesteric does is it doesn't gently go to its ground state. It doesn't start from one twist and then gently somehow add in more twists. It goes through some horrific, complicated sequence of things, and eventually this structure here, in this particular case, was they go to the ground state via the creation of defects, but sometimes this might not happen. And here is my silly simulation. So this is just gradient descent of the director field using the Frank free energy. This system doesn't allow the creation of defects, it's just a director field. And the point is, I don't really want to think about defects, I just want to think about the twisting. And what you see in this particular case is that the system doesn't reach the ground state. So I started with this one twist. I know the ground state is three twists. I know that exactly. But I know that the one twist state is unstable, but it doesn't get to the ground state. It gets frustrated, and it gets frustrated in this sort of quite complicated contoured thing, right? So it starts out with one twist, and then you see that these undulations grow, and then eventually it reaches a metastable state, which is not the ground state. Okay? The energy landscape has multiple minima. And I want to understand, this is the simplest sort of example where you see the sort of packing of layers in a complicated way. And I want to understand generically why the cholesteric can't just then go from here to the ground state. What's stopping it? Okay? And so the actual problem is so hard to study, it's impossible, right? It's a very complicated nonlinear problem. So let's make a simple model of a cholesteric, which is much easier to understand than that one, which is I'll think about cholesterics. I only care about the twist. So I only care about textures which have twist positive everywhere. Equivalently, I can say that there's some f, which is infinity, if there is a point in the domain with 0 a negative twist and 0 otherwise. Okay? So this is an extreme caricature of a cholesteric. I care only that it's twisting everywhere, and I only twisting with the right sign, and I don't care at all about any other elastic property, any energetic property of it. I don't care about how it's twisting, how it's bending, what length scales there are. There's only care that the chirality is right. There's no length scale now in this thing, right? And so now, can I study this caricature of a cholesteric, and can I understand something about the structure of the landscape of cholesterics by looking at this simpler version of a cholesteric? Okay. So basic questions are: with this caricature of a cholesteric, I can say, well, how many minima would I expect to see? So how many different states would I expect to find? And what distinguishes them? Okay? These are not the real questions we want to answer about the physical system, because it's a really simple model. But first of all, we can answer them. And second of all, it turns out that they have a great deal of relevance to what you actually see. So it turns out that the things that distinguish them are things that distinguish actual cholesteric textures. Okay, so mathematically, director field with non-zero twist defines what's called a contact structure. And our classification then asks for a list of topologically distinct contact structures in a given domain. You can also ask for boundary conditions and things like that. Now it turns out that the classification of contact structures is a really, really rich area of mathematics. It's very modern, lots of current work going on. And it turns out there's a huge amount of complexity there, which I guess you can argue reflects the complexity you see in cholesterics. And it allows us to use many new tools that sort of opens the door to a whole world of new techniques you can use to try and understand these structures. And just for reference, these are the pictures that contact topologists draw in their papers. And if you look at those, you see, these are cholesterics, if you're a liquid crystal person. And it takes you see that and immediately think, okay, there must be some connection. But it takes some time to think about it before you actually realize what that connection, how that works. Okay, so the first thing I want to talk about is, in my simple model, I cared only about configurations with non-zero twist. But I can have two configurations of non-zero twist that are close by each other, or I could have two configurations which are separated by some energy barrier, where they have to pass through a region where the twist is not, twist goes to 0. So the first thing I want to talk about are textures in the same class, right, as contact structures. Now it turns out there's a really beautiful theorem by Gray, which tells you that if two textures are in the same class as contact structures, then they're related by diffeomorphism. What that tells you is that if I have a cholesteric which evolves in time. I have a cholesteric liquid crystal which has non-zero twist. It evolves in time, maintaining that condition of non-zero twist. Then there was a coordinate transformation that simulated that temporal evolution, which is to say that I can never tear or rip layers, I can only distort and bend them. Okay? It's a very, it seems trivial, but it's actually a very deep result. This is the idea that you can define these vectors and look at define these layers if you like, and understand how they can evolve under time in the cholesteric. Of course, this is true beyond, it's true generally. Of course, sometimes cholesterics don't have layers, and it's also true in that case also. But it's just nice to draw the pictures so you can kind of see what's going on. So let's do a bit of mathematics in a math place. Okay, so the way that you do this is you say, well, assume the director field is a one form, and it implies that for this coordinate transformation, I should be able to relate the director field before, so the time evolved director field to the original one via this coordinate transformation. This amounts to writing down this equation, okay, which says that the director field at time t is related to the one at time 0. There's a proportionality constant here, and this just comes about because the coordinate transformation might stretch or squeeze space a bit, which changes the magnitude of the director. But we don't care about its magnitude, we care only about its direction, so we're allowing it to stretch, and that's this factor here. And you differentiate with respect to time, and you find this equation. And what does that mean? What am I saying now? If I have this equation, I'm saying, well, if I can show that the time evolution is equivalent to a coordinate transformation, then I should be able to solve this equation. Okay, where W in this vector field W now is the derivative of the coordinate transformation. And it turns out that you can always solve, if you can check, you can always solve this equation with this vector field. And you'll notice that you have 1 over n dot curl n here, which means that if n dot curl n does vanish, this whole thing breaks down and W diverges. So what do you learn from this? You learn that when we set up our silly little model where we only cared about the twist, that all the configurations in the same class are related by a coordinate transformation, which means that all the configurations in the same class have a somewhat similar layer structure. Something looks kind of similar in this regard. And if you want to change the layer structure, if you wanted to go from a cholesteric that looked like this to something that looked like this, you have to pass through a configuration where n dot curl n is 0 in some region. Okay? So far we have shown that all textures within a class are related by a coordinate transformation. But what distinguishes different classes? So we had our silly model, we had different configurations, which have different layer structures that are qualitatively different. And can we find invariants that distinguish them? For example, what distinguishes one twist from 3 twists in the simple cholesteric ground state? It turns out there's a bunch of things you can do. One of the simplest things you can do is you consider a measuring loop in your domain. And the measuring loop has to satisfy the following condition. Its tangent vector must be orthogonal to the director field. Then if you let it flow along this vector field W we defined back when we were doing the coordinate transformation, then this condition is preserved, it turns out. And then it turns out that then because this curve is orthogonal to n, its tangent is orthogonal to n, you can look at the direction that n is pointing along the black curve gamma, and it's always pointing orthogonal. So you can draw this green curve, and the green curve never crosses the black curve because the black curve is orthogonal to n, which means its linking number is well defined. And if this linking number is well defined, it's topological, it's an integer, it can't change, it's preserved under time evolution. And if that's the case, then you can consider a cholesteric between 2 parallel plates, and you look at a curve that goes from the bottom plate to the top plate, and you count the linking number. Now you have to sort of connect them back up, just it's not really a big issue. And then you think about the minimum linking number of all unknotted curves connecting top and bottom plates is a topological invariant of the texture, and in this case, which is really simple, it's the layer number. And to change the layer number, you must untwist the cholesteric, i.e. pass through a region where n dot curl n is 0. So what did we find then? We found that the 1 twist and the 3 twist case are separated by a barrier that has to pass through a 0 twist configuration. So since the 0 twist configuration the cholesteric doesn't like, it has to be sufficient other deformations, distortion, elastic energy in the system to get through that. Of course, this is a trivial example. The layers are obvious. You can look at them and say, clearly there's one layer here and 3 layers there. The point is that this formalism works in general for all twisted Cholesterics. Okay, so we've established through purely topological methods that 2 helical phases cannot be connected without passing through a region of 0 twist. And so I guess I have some conclusions about this. So by thinking about Cholesterics as contact structures, we get a new topological characterization of their textures, of their configurations. And we find that we get this new classes of texture. Each of these classes represent a different type of twisted texture, and they're separated by configurations which have 0 twist somewhere. And you get new topological invariants by doing this of the textures, which include twisting and layer numbers. That was the thing I went through maybe a little quickly just before with this measuring loop. It was a twisting layer or layer number. There's a mathematician, Ko Honda, who has a theory of bypasses in contact structures. And if you look at what he's doing, he's really studying dislocations, actually. So he has a theory of contact structure, these things called bypasses, they're just dislocations. There's this idea of over-twistedness in contact topology, very central and deep idea, which is related to the presence of skyrmions. You can talk about that. And there are more exotic invariants from contact homology theories. The point is, you get all this new topology that comes about if you just think about Cholesterics in this way. And what you typically find is there are a large number of distinct contact structures corresponding or reflecting perhaps the fact that typically you see a large number of metastable configurations for a Cholesteric. Finally, some sort of interesting directions that you could take this in. One is, can you use contact topology to classify defects? As Randy alluded to, the standard method of classifying Cholesteric defects is conceptually incomplete and has some various holes in it. Contact topology doesn't give you a full answer. In fact, it lacks any geometric information related to length scales, but it would be able to tell you something about various twisting numbers associated with defect loops in Cholesterics. And another interesting question, and I think this is also interesting mathematically, is suppose I have 2 minima of the Frank free energy for a Cholesteric that correspond to contact structures of different class, e.g. 1 and 3 twists. I can study the transition path between these 2 states, because there is a path of directed fields between them. It just has to go through a state of 0 twist. Well, this 0 twist region must be created. But can you characterize a 0 twist? How must it be created? Is it a line that it appears on? Is it a surface? Does it pass through the system? Is it just there for a second and goes away? How can you characterize the paths between these different twisted states? And I think that's everything I had to say. So thank you.
Questions? Yes.
So you spoke about the role of the twist deformation, but what's the role of the other deformation?
Well, so yeah, so you can ask, like, so for example, in this, so what I'm studying I'm saying I only care about twist, and I'm saying any 0 twist I forbid. And what happens in reality, you know, where was I had my little movie. What happens in reality is, you know, you have something like this, and it can overcome the twist barrier if the other elastic deformations are high enough, right? Then it could, for example, if the splay deformation is high enough, it can relieve some of that by breaking this condition. And then that's how you pass between the different contact topological classes of texture. Is that?
But could other elastic modes also bring in some essential energy barriers?
So if you did the same thing by saying, I care only that spend is non-zero or splay is non-zero, I don't know off the top of my head if that even is coherent or would make sense, but I think that it would not, even if it did, would not be anywhere near as rich. It's really about chirality and that's the approach.
There was one more question. Yeah.
So this is to both speakers. What is the right way to classify defects?
In Cholesterics, or
Yeah, you both said
so in systems that have translational invariants, the answer is very simple and it was solved in the 70s. In things like Cholesterics and semectics, they're really complicated, and in some limiting cases you can create theories which work. So you can talk about focal conic domains for Cholesterics and say, well, everything's a focal conic domain, but that doesn't work all the time. Or you could think about sometimes there's a mapping between cholesterics and biaxial nematics, and you can think about the defects that way. That also doesn't work all the time. They work sometimes. And there's no, as far as I'm aware, no coherent overall theory which encompasses everything and explains it all at once. And really, they're just very, very complicated systems.
So we need to finish this part of our morning session. Now is the time for the coffee, and we'll reconvene at 11:10. So let's thank both our speakers.